Then we'll start the recording, please. Oh. Maybe we should just wait for Glenn. It's recording. Okay, so welcome back for the second talk in motivic geometry seminar today, and I'm pleased to introduce Lorenzo Mantovani.
Yes, so thank you very much for inviting me to give a talk. So today I want to report on some, let's say, work which is more or less in progress about Chow-Witt rings. Of say the modulus type of curves, of elliptic curves actually, and its compactification. Right, so right, so maybe I'll start with a bit of reminding a bit of the notation that I want to use. So first of all, we will work only over a perfect field, and we will assume that it has characteristic not 2. And when I will mention varieties, and so varieties will be always separated finite type. Right, and so in this setting, every time I remind you very quickly how. So we have Chow-Witt groups, okay, of varieties, and more generally, every time we have an homotopy module, right, we can associate with Roche-Schmidt complex, rather Roche-Schmidt complex on any variety and twisted by a line bundle. So for example, if we start with a Milnor-Witt K theory, then we have the usual, let's say, homological and homological Roche-Schmidt complex on a, say, on a variety X. And twisted by a line bundle L. And similarly, if X is smooth, we have a homological version and for example, this complex associated with X and the jth part of this homotopy module twisted by L is just the complex concentrated in degrees, in homological degrees 0 to D, where this is the dimension of X, right? That starts with K, J of the fraction field of X, twisted by L. Then it continues with Kj minus 1 of the residue field at points of codimension 1. So the sum that I got it right. And twisted by M mod M square dual, and then transferred out. M mod M square was, of course, the maximal ideal at the local ring of small x inside our variety X. And then we keep going all the way to, well, until X is exhausted. So associated to these two Roche-Schmidt complexes, we have respectively homological and cohomological Chow groups. And in general, we have Chow groups with coefficients, or rather Chow-Witt groups with coefficients, which are basically, which were defined by Rost first, and then by, in the Witt version, by Feld recently. And we will only deal with cohomological groups today. So I will just maybe write this. So IX twist L to be defined as the ith cohomology group of the complex associated to X minor Kj, minor with sorry, Kj, Ki, sorry, and twisted by L. Right. So in principle, one should be careful with twists and really twist by graded line boundaries rather than just line boundaries. But today we don't have so much time to be precise on these details. So I just try to outline how the theory should work. Okay. So this is it. And maybe a quick remark is that first of all, that Chow-Witt groups sit in a sequence which presents them as an extension of two groups, right? And on the right-hand side, we find this thing that I call PIXL, which is nothing else than the pullback of the Chow group fibered over the Chow group mod 2 of with the cohomology of the fundamental ideals in twist L. There was an I here, so this is an I, this is an I, right? And the kernel of this map is also explicitly understandable. So there is an explicit formula for the kernel, but now we don't need this explicit formula because I'm not telling you about all the proofs. The only thing that you need to know is that this QI is actually a quotient of the two torsion of the ith Chow group. So in particular, if the ith Chow group has no two torsion, the Chow-Witt ring is just a pullback of Chow ring over the Chow ring mod 2 with the IN cohomology. Okay, right. Very well. So with this on our, so with this observation in our pocket, we can keep going with a bit of a reminder on the equivariance theory that we need to deal with M1 and M1 bar. And so what about the equivariance theory? So well, you know that for Chow groups, there was an equivariance theory developed by Totaro and Edith Ingram, which is equivariant in the sense that it's more of a Borel equivariant theory in analogy with topology. So this is a Borel kind of, so this is after Edith Ingram, and it's a Borel kind of cohomology. Okay, and so this Borel type of theory can be extended without any effort, let's say, to Chow-Witt rings. And we just give the following definition. So now I assume that G is a fine group scheme. And that X is a smooth variety. Just because I want to use the cohomological version of Chow-Witt groups, but I could also place something singular. It wouldn't be a problem. Just I would have to use homological groups. And we define in this setting, we define Chow-Witt rings, but then I have to also to take a G-line bundle on X. And as I said, Chow-Witt ring, Chow-Witt group, at least in codimension P of equivariant with respect to G with coefficients in L. Is defined as follows. So for Chow, group of cycles of dimension P of a certain scheme UV cross X and then quotiented, so with the diagonal action, and then quotiented by G with coefficients in L, where UV is open inside the representation of G defined over K. Okay. That satisfies a number of assumptions, okay, which are the usual ones. So the assumptions are mainly the following. So the complement of UV in V, which we call SV, is of course closed and it's G-stable and of codimension strictly bigger than P+1 if we want to have cycles of codimension P. What else? UV, the action inherited by UV should be free, which guarantees the quotient of UV by G to be an algebraic space. And then some maybe more technical assumptions that we will not really care very much today about, and it's that the quotient should be also not only an algebraic space but a variety, and that when we further take this mixed quotient, so X cross UV quotiented by G, this should also be a variety. Okay, so there's a lot of assumptions here, but the important thing is that the first three things are about our assumptions on V, okay? And we can always find for every given codimension P, a representation with an open subset that satisfy these assumptions, okay? That's not so difficult. And regarding the last two assumptions, what I can say is that they're kind of needed to ensure that we're taking the Chow group of a scheme, but I think that they're not really necessary. So one probably can extend the theory to algebraic spaces. And so I don't claim that I can do it right now, but I don't think they're really necessary. Okay. And anyway, today we will not worry about these ones because G will be either GM or a group of roots of unity and invertible in K. And in both these cases, quotients always exist in the category of schemes. So there's not really, so we don't have to worry. Okay. Okay. So right. So I'm doing with time 15 minutes. Okay. So maybe a couple of remarks are that no, this definition looks very ad hoc, but actually it does not depend on any of the choices that are made. And actually the definition only depends on X and G. And actually, to be honest, only depends on the quotient stack X mod G. Okay, meaning that if you have another quotient stack of Y mod H and the quotients are isomorphic, then the Chow-Witt groups with coefficients are isomorphic. Okay, and this is the usual. The proof is the same that you use for Chow groups. Okay, so right, so maybe I'll just erase this. Okay, so this definition seems to depend on a lot of choices, but it doesn't. Okay, and very well. So in practice, one really wants to say that this Chow-Witt ring or group that actually we have defined XL is actually the Chow ring group of the quotient stack. With now, of course, I'm kind of identifying G line bundles on X and line bundles on the quotient. Okay. Good. So an example of how these things, what kind of information we can find in these groups is basically was computed by Fazel and Matthias Wendt, and it's the Chow-Witt ring. So together with the multiplicative structure of the GM with coefficients in a line bundle. And this is, well, of course, it's an algebra over the Grothendieck ring of the base field. It has two generators as an algebra, and there are some relations that I will write later. So T is the Euler class of O. Now I have to make a choice, and I think I'll choose -1. So is in by degree, so cohomological degree 1 and twist O1. And H is a sort of twisted version of an hyperbolic class. So it's more or less an artifact of how the theory works, and it's in by degree 0 O. Okay. Good. And the relations are very easy. They say that the fundamental ideal kills H, kills T, and that H is somehow an hyperbolic class in the following sense. Okay, good. So this is an example is important because since what we do today is anyway GM equivariant, it means that all the Chow rings that we will see today are algebras over this Chow ring that I just wrote down. So T and H will keep being around for the next 15 minutes. Right, and so
does that say that T is in by degree 1 with twist O of 1? What's the degree next to T?
Yeah, it's 101.
Great.
Because it's associated to a divisor, and it's the twist of when you have an Euler class, you always land in the twisting by the dual of the line bundle. Does it make sense?
Yes. Yeah. No, I'm with you. I couldn't read. Thanks.
Yeah. Sorry. I have to apologize. My computer is about to explode. Actually. Okay. Good. Very good. So this is it for the Chow ring of the GM. And let's see. Let's try to. I'll write. Do I write this formula? Well, let's try to keep going. Maybe I'll talk about M11 before I run out of time. So let's go to M11 and M11 bar actually. So let's see. So this. Okay. Now I should really say this. I think I forgot to say at the beginning, so I will say this. I will maybe make it very clear with a very thick pen that this work is, so this part of the work is joined with Andrea Di Lorenzo. So I actually should have written this basically directly at the beginning. Okay, so what should we say about M11 bar? So, well, first of all, is that, well, I don't remind you the definition. So this one classifies stable curves of genus 1, pointed stable curves of genus 1, and this classifies elliptic curves. And we consider them as stacks. Let's say the Riemann for stacks over K. Okay, they're actually defined over Z. And maybe the first thing that we should remember is that one can construct them, at least if the characteristic of K is different from 2 and 3, one can construct them in a rather explicit way just by saying that M11 bar is what is it? It is the quotient of an open subset of a representation. So it's a representation of GM, where GM acts by weight -4 and -6 on the two coordinates of A2. We remove the 0 of A2, which is G-stable, and we take the quotient by GM. And maybe this is an isomorphism, okay? And the idea is, well, I guess this is not difficult to prove. Just when you take an elliptic curve, the usual Riemann-Roch argument in characteristic different from 2 and 3 tells you when elliptic curve or even a stable curve in characteristic different from 2 and 3 gives you an embedding of the curve into the projective space bundle associated to the relative forms. And what you get is an equation with two coefficients, and the two coefficients are basically the two coordinates of it. And then this equation is not unique, but it's unique up to rescaling. Okay, so here's where the GM comes up. Okay, so this is it, and M11 is just open inside M11 bar, and it's again an open of A2 minus 0, but actually is the complement. Is the complement of the locus where the discriminant is equal to 0. So I'll just write it like this, where delta is now, oh, I forgot to, it should be, if I remember correctly, it should be something like this. Okay. Right. There is actually some other coefficient that can be ignored. I think there is a 16 somewhere, but we ignore it since we are in characteristic node 2. Right. So this basically, this description tells us pretty much how to start, right? How to start computing the Chow-Witt ring. But before we start, maybe I'll just write the result. And I'll write it like this. So, so the Chow-Witt ring in degree star of M11 bar and in weight bullet is a GWK algebra with three generators. So T, H, and how did I call it? B, with some relations. Now T is pulled back from BGM, okay? And it corresponds to the Euler class of the line bundle on M11, which is the push forward of the relative forms from the universal elliptic curve to M11 bar. Universal stable curve. Sorry, I'm actually calling elliptic curve even a singular one. I hope you can forgive me for this. So stable curve to M11, that's a universal curve. The dualizing sheaf of the family push forward is a line bundle, and I can take the Euler class. And actually comes from BGM. H has the same meaning as before. So at V now is a bit more complicated to explain, and it can be taken to be the push forward of some class E from B mu2, and I is the embedding of B mu2 inside M11 bar as the locus of singular curves. So is the locus where delta is equal to 0. Okay. Right. So I haven't told you what the class E is because I haven't told you what the Chow ring of B mu2 is, but I'll come back to that later. Okay. So maybe I'll just write like this: A lives in H0 B mu2 GW, and this is the ramified sheaf associated to GW theory. Okay, it's something related to discriminant. Let's call it discriminant. Okay, and so these are the generators as an algebra, and then I should write you some relations, which now start to be a bit annoying, but let's do it. So as you could imagine, IT and IH will have to be 0. And H square will have to be 2 times the hyperbolic class. And now there's all the relations that relate V with the other generators, and it's that HV is equal to 0, big HV is equal to 0, V squared is equal to minus 2V, and then the 2 most important ones, which are that 24T squared is equal to 0. And to be more precise, this 24T squared should be written really as a 6H squared T squared, because in this way we clearly see the relation between this number and the product of the Euler classes of O minus 4 and O minus 6. And the last relation is that 12HT is equal to 12HT squared is equal to BT. Okay. Right. Maybe I should also spell out that V lives in by degree 1 and twist O. Good. So by this huge amount of symbols, I mean that, well, okay. So these are all relations that hold in this ring, and you should take the ideal generated by this bunch of things that I wrote down. Okay. So now my time is over, and maybe I'll take 1 minute to outline the proof, if you let me. So an outline of the
proof. Go ahead. No problem. Go ahead, Lorenzo.
Okay, it'll take very few minutes. Okay, so maybe I'll divide it in. I'll just sum up the 4 steps that I wrote down earlier. So maybe step 1. So basically starts from the GM equivalent geometry of these representations of A2 minus 4 minus 6, right? Which basically tells us that M11 is open inside the vector bundle of rank 2 over GM. So there's this vector bundle over BGM, and it has an open subset, which is isomorphic to M11 bar, and there is the complement is the 0 section of the bundle. Okay, and now when you do equivalent Chow rings, we've seen you have to find a representations of GM that let you approximate all the spaces that you have here. So it's quite easy because this, so GM is approximated by a projective space, right? And so this vector bundle over GM is approximated by the total space of O minus 4 plus O minus 6, right? So it has a 0 section, and necessarily M11 bar is then represented by the complement, is then approximated by the complement of the 0 section. Okay, so if I call this B, then this is B minus the 0 section. So using this the localization sequence associated with this decomposition, plus the fact that homotopy invariance and the fact that we know we know the Chow ring of BGM, we get a, say, localization sequence. Localization sequence that basically identifies the Chow-Witt ring of BGM, twist, so degree star and twist bullet, modulo 24 t squared, which is exactly the Euler class of this vector bundle, as a subalgebra of the Chow-Witt ring that we're interested in, of M11 bar. Okay, and the localization sequence, as you know, continues on the right with the cohomology, with bit cohomology of BGM. But what you find is that actually the localization sequence almost always stops. And so there is only one degree, and this is step 2, in which question mark is different from 0, which is by degree star equal 1 and weight equal O, okay, in which question mark is actually isomorphic to the Witt ring of the base field. Okay, so this means that the localization sequence determines all the generators except for one, which sits in by degree 1, 0, and it's more or less the V that I gave in the statement. It's not exactly that, but up to it is that up to a unit of the Witt ring. So, okay. Anyway, so this basically tells us that a generator, so a generator of this Witt ring, together with the generators of the Chow-Witt ring of BGM, give us generators for for the Chow-Witt ring of M11 bar. This gives us all the generators. And now, in terms of relations, the relations are a bit complicated. So, step 3, if you want, is realizing that using the equivalent geometry of the representation that I outlined above, one can actually compute the whole Chow-Witt ring of M11 without bar. So, okay, you don't need to compute the whole of it, but you actually need to look, you only need to check what is there in by degree 1 and twist O. And this is actually isomorphic to Z mod 6 HT, okay, where HT are the classes pulled back from BGM. So one only needs this this equality, but one can actually compute the whole gadget actually. And step 4, to conclude, is to look at the localization sequence associated with M11 bar, the open subset M11, and the closed complement mu2, which correspond to, as I said, delta, so discriminant non-zero and discriminant 0, and see that the class that now we have defined earlier, so basically picking up a generator of WK and choosing a lift here, okay? Well, that class, if you choose the lift smartly, comes, so lives here, first of all, So maybe, so we chose a class here in this question mark. We lift it here, choosing the lift smartly. And in by degree 10, this class actually lives here. Okay, I don't really have time to write it down, sorry. And so what you can see is that this class will have to die when you restrict to M11. And so this class does actually come from BMU2. Okay, so the class, let's say B prime that we found here, suitably lifted, has to come from here. Could it be double prime? Okay, and actually one can, up to changing things by unit in the Grothendieck bit ring, which we don't care so much of, we can actually replace this class over here by a very explicitly defined and very explicitly constructed class, which I called E earlier, and I haven't really said what it is. Okay, but the moral of the story is that now that you know that your extra class comes from BMU2, all the relations that you needed to check for the ring structure of M11 bar via projection formulas can be reduced to checking relations in BMU2. And checking relations in BMU2 is much, much easier and can be done by hand. And this is actually how it works. You compute some intersection products by hand and you find the result. So, and now, oh wow, super over time. So this is it for the proof. And maybe the upshot is, right, so the upshot is that, well, which I haven't mentioned actually, is that if you look at the equivalent geometry of the representations that we mentioned, is that we can actually compute the Chow-Witt ring of M11 without a bar, and it is actually the same as the Chow-Witt ring of BMU12. And the identification is given basically by pulling back along the discriminant. And actually, what I think is true is that the two spaces, the two, say, equivalent motivic spaces associated to the two, to the two stacks are actually one equivalent. And in particular, not only the Chow rings of M11 and BMU12 will be the same, but actually all motivic invariants that can be phrased in terms of GM equivalent SH would have to be the same. Okay, so that's it. Thanks for listening.
Okay. Okay, thanks a lot, Lorenzo. Seems like great work. So, isn't the Picard group of this modelized stack is cyclical order 12? Does that help us to see some of these relations? Then?
Right. So the Picard group of M11 is a degree is a cyclic of order 12, and if you want here you already see the relation why delta comes in, because it's cyclic of order 12 exactly because there's a generator, which is this push forward of the relative forms from the universal curve. This is a line bundle, okay, on M11, and the discriminant of the elliptic curve, said in a fancy way, is a trivialization of the 12th power. Okay, and giving a map to BMU12 means exactly giving a line bundle with a trivialization of the 12th power. So the discriminant of the elliptic curve essentially associates to every family of elliptic curves a mu12 torsor, and that's exactly the map that realizes the equivalence. Maybe I should remark that all these things are about to be written in a preprint. The preprint is almost ready, but maybe you should take it with a bit of a grain of salt before it is actually uploaded on the archive. But I'm reasonably comfortable that there are no mistakes, just for someone being honest. Okay. Any other question?
Higher G's and M's, MGN. I know that's a little bit unfair, given, but Chow-Witt of MGN comments. Yes, unfair. I agree.
And so I think the first, so if we continue in this direction, there will be something on M2, which is somehow can be also somehow worked out with a bit of somehow with playing around with representations, and maybe there's some direction on the moduli of stable curves of genus 0, stable maps, sorry, of genus 0. There's some, okay. I think an old description, not so old actually, of Kiel maybe, that gives generators and some relations. They're a bit awkward, but there is a kind of streamlined way of writing them. But yeah, I cannot claim anything so far. So far we have only looked at M1 now.
Nice.
Right. So yeah. Maybe I should advertise one thing that in general. So we have done some work on cyclic groups too, and yeah. So this is also, so what you've seen is completely joined with Andrea, as I said, but for cyclic groups, actually for mu12 and well, not for mu12, let's say, but for mu2. That is used a lot in the proof, even if it's not clear. If I didn't make it clear, work on mu2 has been done with Toan and with Matthias Wendt. So the joint work with them allowed us to somehow to have a very clear understanding of mu2, and with somehow what happens in some, I mean, how to write this kind of formulas in a cheap way, okay, in a quick and say without too many generators and without too many relations.
Okay, great. Any other questions? Doesn't seem to be the case. Let's all thank Lorenzo again for a very interesting talk.